Hi, good evening, students. How are you? And say hi. Many of the students are actually waiting. It's good to see all of you guys. Am I audible? First of all, if you could make it clear, we will go ahead. Shall we start? Yes, Kirti Suresh, and who else? Whoever? Lokesh Parab. Yeah, good. Um, the regular students. Good evening, Lokesh Parab, Kirti S. Kumar. Yeah. Good evening. So, last week we discussed about how to solve gate questions, right? This week I am going to take you people somewhat ahead. Okay, so we are going to discuss about the instruction formats with respect to the location of the operand. Okay, again just let me tell you, last week we discussed about how to solve the gate questions in instruction set architecture topic. Now, in the same instruction set architecture topic, we will move a bit ahead. Okay, we are going to discuss about the instruction formats rather, instruction formats in terms of the location of the operand. What is the instruction formats in terms of the location operand? How we are going to go through it, and just don't worry. I'm going to make it very clear. The only thing is you should be focused and you should be able to follow me very carefully. I'll make it very easy for you guys. Is that fine? Yeah, good. Now, the topic is we're going to discuss about instruction formats with respect to the location of the operand. Yeah. Now, the thing is, when we talk about the instruction execution, I told you guys that for every instruction, there will be some operands, right? If you want to execute an instruction, we do need operands. Yes or no? We do require operands to be collected in order to execute any instruction, right? I just want you people to follow me. Okay, even if you join, I mean, even if you are attending the class for the first time, doesn't matter. I'm going to make it very clear for you people. Okay, I'm going to keep it in my aspect that there may be a newcomers also, so I'll make it very fresh, and I'll explain in such a way that even a newcomer will be able to understand it very easily. Okay, so now answer the question. We do require the operands to be collected if we want to execute an instruction. In other words, every instruction requires operands, right? So here I'll put it this way. Instruction needs operands, right? Okay. Here, this is very clear that every instruction needs an operand. Okay, now we are going to talk about the instruction formats. Let me write it here. Instruction formats. Okay, here these instruction formats will tell you from where the operands are needed to be collected. That is, I'll put it this way, instruction formats, I'll keep it in the brackets, in terms of location of the operand. location of the operand. Okay. Now listen to me. There are a few instruction formats. There are a few different instruction formats in which operands can be collected from the different parts of the computer system. Okay. Am I audible first of all again? Am I making it myself clear? Lokesh, Parag, Kirti, just answer to me. Now I am talking about instruction formats. If you want to execute an instruction, this instruction requires an operand. Okay, now we need to supply the operands to the instruction. So the instruction formats when you talk about with respect to the location of the operand, the operands for an instruction can be collected from different parts of the computer system. That is all about instruction formats. Mainly there are three instruction formats. Let us stay focused. There are three instruction formats. Three instruction formats. Three instruction formats. Okay. So here the first one is, let me tell you, memory reference instructions. I will explain it completely. Just identify the terms. Memory reference instructions. Okay. Second thing is register reference instructions. I'll put it here. Second thing is register reference instructions. Okay. And the third one is IO instructions. IO instructions. The first one is memory reference instructions. We have a total of three instruction formats when it comes to the location of the operand. Those are memory reference instructions, register reference instructions, and the IO instructions. Okay. Now, I'm just going to make it very simple. I'm not going to take more than 1 minute to explain what are memory reference instructions, register reference instruction, and IO instructions. Let us stay focused. When it comes to the memory reference instructions, the operands will be collected from main memory. Okay. If for a particular instruction, the operands are available in main memory, those instructions are called memory reference instructions. Okay. So that means if you want to execute that specific instruction, operands must be collected from the main memory. For those instructions for which operands are available in main memory, then all those instructions are called memory reference instructions. Okay, this is the first classification of the instruction format. The second one is register reference instructions. If you want to execute a few instructions, operands will be available in the processor's registers itself. You don't need to go to the main memory. Okay, are you here? Kirti and Lokesh, are you here? If you want to execute a specific set of instructions, those instructions may have their operands available within the processor's registers itself. Am I audible? I mean, you people are not participating. I just want to understand why. Am I audible? Am I not seeing anything? Yeah. Fine. I am in the chat box. I don't know. It has been stuck. Yeah. I got it. I got it. It has been struck. My YouTube has been struck, so I was unable to go through the chat. Fine. Operand operators are this. No. I'm not talking about the operator. There are several questions. I didn't go through these questions. Let me answer. Let me address these questions first of all. Okay. So here I do have a few doubts. We need operands and operator. See, I'm not talking about the operator. Let us forget about this concept of the operator for a while. We are not, doing any math here. We are not solving the mathematics sense. Okay, we will just talk about operands only. Okay, you'll understand completely. Next thing is Kirti's doubt is it needs operator. Operator, you keep it aside. Now, operand and operator. No, operand is different and operator is different, but we do require an operand to execute an instruction. Yes, it is audible. Sir, I think you are not viewing the live chat. Of course, I was watching the live chat, but it was stuck for a while. But fine now. Okay. Now, let us stay focused. Now, everything is fine. Answer me. There are men. What are the locations in the computer system in order to store something? I do have three things. If you want to store something, I need some memory forms. The first memory form is obviously processors register. Second memory form is obviously main memory. Okay. If the operands are collected from main memory, then these instructions are called memory reference instructions. If the operands are collected from processors register, then these registers are called register reference instruction. Okay. Now again, just put a message so that I will be able to understand you guys are good. Okay. Now let me completely explain you this. You forget about operator concept. Now we are not talking about the programming languages. Okay, we are talking about the machine language instructions. Machine language instructions for which, if you want to execute, you require an operand. Now our only problem and concern is from where to get this operand. Three locations: main memory, register, IO devices. Okay, let us stay focused. You remember about our instruction? The instruction for the computer system that we are designing is of 16 bits, right? Instruction is of 16 bits, right? For the computer system that we are designing is equal to 16 bits. Already I divided these instruction into three fields, right? The instruction has three fields in it. Okay. First bit is called mode bit. Okay. This is the most significant 15th bit. And then there are three digits given to the opcode. 12 to 13, sorry, 12 to 14, 12, 13, 14 digits are opcode digits, right? Least significant 0 to 11 are the memory address of operand, right? Just a small recap. The instruction is of 16 digits, total is equal to 16 digits, okay, in which the first digit is the mode digit. The mode could be either direct or indirect. Okay. And then there are three opcode digits. 12, 13, 14 are given to opcode, and 0 to 11. A total of 12 digits are given for the memory address, or rather, the address of the operand, which is available in a specific location of the main memory. Why we got 12 digits here? Because our main memory is of 4096 locations. So if you want to represent one of the address in 4096 locations, I do require 12 digits. So that has been assigned to a memory operand. Now I do have a few questions. Just answer me. Okay. So I will make you people, I will make you people completely getting this concept comfortably. Just answer to my questions. Okay. How many digits are given for mode? How many digits are given for mode? Array mode, not for instruction. 15th digits. Excuse me. Madam, Lokesh, sir, Kirti, you gone completely wrong. What happened to you? Only 15th digit is the mode digit. Okay, so my question is, I did not ask you which digit has been given to the mode. My question was, how many digits were given to mode? Only one, right? Kirti, I want your answer so that I'll go ahead. Good. Okay. By using one digit, how many modes are possible? By using one digit, how many modes are possible? Two, right? Because one digit can give you two combinations. 0 is one and 1 is another one. By using one digit, there are only two possible combinations. 0 will give you one mode, 1 will give you another mode. Already you know that. 0 is direct addressing and 1 is indirect addressing. Right? Forget about it. We are done with the mode. Okay. Now let us take opcode. Okay. How many digits are assigned to opcode? How many digits are assigned to opcode? How many digits are assigned to opcode? 3 digits. I want Kirti, you also need to participate. I just want both of you guys to answer to my queries rather quickly, so that we'll go ahead rather quickly. Yes, very good. Now, by using 3 digits, how many opcodes are constructed? How many opcodes can be constructed rather by using 3 digits? Lokesh, perhaps good. And I just want a final answer. Kirti, by using 3 digits, how many opcodes can be possible? Very good. Lokesh, perhaps 2 power 3, those are equal to 8. Yes or no? Kirti, answer. By using 3 digits, we got 8 possible combinations from 000 to, because 2 power 3 is equal to 8. Very good. Now stay focused. Here, you yourself answered me that our computer system can support a maximum of 8 machine language instructions. Yes or no? You yourself told me that our computer system can support a maximum of 8 machine language instructions. Didn't you? Yes, you did. Because in our instruction format, opcode is of just 3 digits. Okay. In the current computer system, we do have a 16-digit instruction. But if we just locate this opcode, we do have only 3 digits. That means that in our computer system, the maximum possible machine language instructions or opcodes or whatever you call are just 8, right? Yeah, sir. Due to low network bandwidth, and I got your problem. So, but fine. Okay, but okay, you keep on doing your business. Keep on sending your messages. So I will understand. Okay, even if it is a bit late, doesn't matter. No problem. Okay. So here, I'll write it here. The combinations are 000, 001. Okay. 010, 011, 100, 101, 110. Am I right? Am I right? 1, 2, 3, 4, 5, 6, 7, 8. 111. Okay. So total 8 combinations. 1, 2, 3, 4, 5, 6, 7, 8. These are the possible 8 combinations for which each combination there can be an encoded machine language instructions. Okay, being a designer, first of all we need to identify how many combinations are available for, what is the number of digits for the opcode. The number of digits for the opcode is equal to 3. So for a designer, 8 machine language instructions can be encoded to all these each possible combinations. combinations. Being a designer, first of all, we need to identify the possible combinations. For each combinations, a designer can encode and assign one machine language instruction. Okay, triple one. Yeah, of course, triple one I have written. 00001 Yes, triple one also I have written. Fine. Now stay focused here. All of you. 1, 2, 3, 4, 5, 6, 7. Now you just, for a moment, you forget this triple one combination. Okay, for a moment, you forget this triple one combination. So how many are available? Total 7 combinations. Okay, so just stay focused. How many we do have? The instruction formats. We do have 3 instruction formats: memory reference instructions, register reference, and IO instructions. Okay, you forget this triple one for a while. Okay, now remaining all from 000 to 110 are assigned to memory reference instructions. Okay, from in our system there are a total of 7 memory reference instructions. The combinations are from 000 to 110. Am I making it myself clear? There are 3 instruction formats: memory reference instructions, register reference instructions, and the IO instructions. I do have 8 combinations. Forget about 8th final combination, that is triple one. You don't bother about it right now. Just only the first, look at the first 7. Okay. Memory reference instructions are going to occupy all these 7 combinations. For each combination, there is a memory reference instruction encoded. Got my point now? There are a total of 7 memory reference instructions. Okay. And triple one is not assigned to memory reference instruction, which means that triple one can be either a register reference instruction or IO instruction, right? IO instruction. Let us go slow so that you will be understanding. Triple one is not assigned to memory reference instruction. Apart from except triple one, all the other combinations assigned to memory reference instruction. Okay. Now let me explain all those instructions which are memory reference instructions. Let us talk about memory reference instructions. Okay, I am going to give you all the memory reference instructions right now. Just keep it in your head or write it somewhere, but this has to be digested completely. There are a total of 7 machine language instructions from 000 to 110. 111 is not a memory reference instruction, which means that this when you have 111 combination in the opcode, that could either be a register reference instruction or an IO instruction. Got my point? Now let us stay focused. I am going to explain you all the memory reference instruction in the system that we are designing. Let us stay focused. 000 is assigned to end. Okay, you know what is an end instruction? End instruction is an end instruction. I don't need to explain you what is an end instruction. When end instruction is getting executed, an end operation is going to be performed. I guess you guys don't want me to explain you what is an end operation, right? Yes or no? So 000 is assigned to end. Okay, then 001 is assigned to add. Okay, very good. Obviously, I expect you guys to know what is add also. AND is a logical instruction in which 2 operands can be ANDed. Okay, AND operation requires both digits to be 1 in order to have an output 1. Even if one of the digits are equal to 0, then the output will be 0. So fine, you know that anyhow. Add is not a bitwise operator. Add is not a bitwise operation rather. Add is going to perform addition, in which 2 weighted numbers will be added. You know what is a weighted number? From a respective bit position to another bit position, weight will get changed. There are several weights, binary or gray code or octal, 2, 4, 8, 16, rather, whatever. the aids will be different from code to code. 2424 or 2468, there are several weighted codes. Add is going to perform an addition between two weighted codes. Okay. What is this not change, sir? Yes, you should remember. You should, yeah, understand something. Are you here first of all? Are you listening to me? Just answer to my question. Are you listening? Kirti and Lokesh. Very good. Now, we are designing a computer system, right? We are designing a processor. If you remember, right from the first week to now, what we've been doing? We are designing a processor. Okay. This processor has a unique set of features. It could be, any processor. That is, it could be Intel i3 or i9 or i7. Just imagine that it is a processor in which there are a few instructions. If you could understand this, tomorrow you can update this processor to any level processor. I hope you got my point. Did you get it? Okay, this is a basic processor. If you could understand the design and architecture, then any other processor, any updated processor will be a cakewalk. If you want to update this processor to any other processor, it will be a cakewalk. It will be crystal clear and very easy. Okay, so in our system, the first 7, that is 000 to 110, the opcode combinations are assigned to memory reference instruction. 000 is given to AND, 001 is given to AND, 010 is to load. I'll explain what is the load instruction. I explained you guys for several times, but one more time I'm going to explain what is the load instruction. 011 store. Okay, and then 100 is an important instruction which is called BSA. What is BSA? I'm going to explain maybe in upcoming sessions. There is another instruction called, which is very next to, which is positioned next to the BSA instruction, that is BUN. But I can explain you the full form right now. BSA stands for branch and save the return address. BUN stands for branch unconditionally. If you remember, while I was explaining stack, I took the help of BSA instruction, but don't worry, I am going to explain once again how this BSA instruction is going to work, as well as BUN instruction. Okay, and there is another instruction called 110, that is ISZ. Okay, now stay focused. BUN is branch unconditionally. ISZ stands for increment and skip if 0. BUN, listen to me, I am going to explain you, Kirti. Don't worry, you are going to understand to the level I want. You don't worry, I am going to make you people perfect in computer architecture. Only thing is just follow me, that's it. Okay, and is end. What is add? Add is add. There is nothing more. Load and store. Load and store we're going to discuss right now. Okay, in this session itself. BSA stands for branch and save the return address. BUN stands for branch unconditionally. Okay, ISZ, increment and skip if 0. Write it somewhere. Increment and skip if 0. This is all about ISZ instruction. Okay, now stay focused. I'm going to take you one more step ahead. Okay, so here let us look at our instruction format again. Yeah. Here, first digit is mode and the next 3 digits are opcode, right? Yes or no? First digit is mode, next 3 digits are opcode. Yeah. Here, we are talking about memory reference instructions, right? Okay. What do you mean by memory reference instruction? If it is a memory reference instruction, for all these instructions, operand will be in main memory, right? Operand will be in the main memory, right? Okay. I'll give you an example. I'll give you an example here. So here, I will say directly add. I'll put it add here. Add. I'm not writing the combination. If you see add, it should be equal to 001. In the opcode, it has to be 001. 001 meaning add. Directly I'm putting add here. So add, let us say 450. What is 450? 450 is a 12-bit address which is available in the address part of the instruction, right? So now I just want you to continuously be with me and answer for every question I ask. Even if I ask you yes or no, you just have to put yes so that I will go ahead. Otherwise, you just stop me when you have a doubt. I will be halting there for a while and then I'm going to pause myself to explain you the doubt. Then I'm going to raise you. Is that fine? Now, for all the memory reference instructions, there will be a memory address within the instruction. This memory address is going to show the address of the operand. That means that, okay, that means that we need to go to main memory. Which location it is? 450th address. In 450th location of the main memory, the value is available, that is 150. You already knew this. I don't need to explain you more. As you said that in main memory, some part of the main memory is allocated to the system. Forget about that. We are not talking about the operating system. What do you call, the detail is immaterial right now. Okay. Now only the thing which concerns us is how to get the operand. Okay. The operand will be available in the 12 bits. Okay. In this 12 bits, we do have an address. Taking this address, we need to go to the main memory. Is this the direct value? No. This is a memory address in which the operand is available. Right? Already the second operand. Yeah, I do have a question. I do have a question. What is the second operand? What is the implicit operand in the single accumulator organization? Remember, location Kirti. What is the implicit operand? What is the implicit operand here? Yeah, what is my question is? My question is, I do have only one operand. Here I do require second operand, right? Array, come on, accumulator man. Accumulator is equal to accumulator plus m of 450. You can't say no idea if you've been following me from as many weeks as you are. You remember? In the single accumulator organization design, very good. The second operand is always accumulator, because if you want to execute an instruction, if you want to perform an operation, I do require two operands. Our instruction will provide you with only one operand. Second operand is always accumulator. Got me? So, second operand is always accumulator. So, which means that accumulator is equal to accumulator plus memory of 450, which is equal to 150. Right? Yeah. So, here for memory reference instructions, this mode could be either 0 or 1, right? Okay. 0 means direct, 1 means indirect. Yes or no? For memory reference instructions, mode will be either 0 or 1. Okay. Any memory reference instruction, it could be end or add or load or store or whatever. Mode could be either 0 or 1, because if it is 0, directly it is 150 is the what do you call the operand. If it is 1, it's an indirect address. In 450, there will be one more address. Again, we need to go to another address to this 150. In 150, the actual operand. We've been discussing this for almost 2 decades, many decades. So here in 150 we are going to have this operand. I'm not going to explain this because mode I've been explaining you for since so many days. Got me? This is what you call 50. If the direct addressing mode, the address of the instruction is going to provide you with the direct address in which the actual operand is available. In the indirect addressing mode, if the mode digit is equal to 1, the address of the instruction is going to give you an address in which there is another address. Okay, in this address there will be the actual operand. This is the thing. So for all the memory reference instruction, there will be mode. Okay, this mode is also called addressing mode. The address could be either direct address or indirect address. Now, stay focused all of you carefully. Not only memory reference instructions, we do have two different instruction formats also in our system. What are those? Register reference instructions or IO instructions, right? In addition to memory reference instructions, register reference instructions or IO instructions. We do have two other instruction formats along with memory reference instructions, right? Can you tell me yes or no? In addition to memory reference instructions, I do have register reference instructions and I also do have IO instructions. So when it comes to memory reference instructions, the combinations right from 000 to 110 are used. Okay, but for a memory reference instruction, 111 combination is not used, which means that okay, when a particular instruction is getting executed and in the opcode field the combination is 111, then definitely it is not a memory reference instruction, right? Okay, in the opcode field, anywhere in between 000 to 110, if the combinations are existing, you can tell me that, sir, this is a memory reference instruction. But when you see in the opcode the combination of 111, then definitely you can say, sir, this is not a memory reference instruction. Then I'll ask you, then what is opcode? Then this what instruction format it is? You can tell me that, sir, it could be either a register reference instruction or an IO instruction. You will tell me, yes or no? Now my question is, okay, fine, 111 combination will be either a register reference instruction or an IO instruction, but it cannot be both. It can be only one, right? How you can give me register reference if it is the register reference instruction or an IO instruction? Let me tell you. Okay, to make it very simple, for only memory reference instruction, I do require a mode, right? What do you mean by mode? Mode is just nothing but an addressing mode. If it is not a memory reference instruction, there won't be any memory address. Got me? If it is not a memory reference instruction, we don't need a memory address because we are not going to memory. If we do go to memory, then only we do require an address. Okay. If we don't have an address, we won't have mode also. This mode will talk about its address. If we don't have an address, we won't have mode also. Got my point? Only for memory reference instruction, I do require these two fields. This mode will give you addressing mode. These 12 digits will give you address. If it is not a memory reference instruction, there won't be any address in the instruction. There won't be any mode in the instruction. Okay, which means that I can use these two fields for different purposes. Okay, I'll tell you what are those purposes. I am left with only one combination, that is 111. Okay, so what I'll do is I will use the mode digit. 111 meaning it is not a memory reference instruction. Okay, so what I'll do is, in order to differentiate between register reference and the IO instruction, I will use this mode digit because anyhow I don't have an addressing mode. Okay, so what I'll do is I will use this mode digit to differentiate in between register reference and the IO instruction. So I will use 0 for register reference instructions. Okay, so a combination of 0 111 will tell us that this instruction is a register reference instruction. Okay, in the opcode again we do have 111 with a mode digit which is equal to 1 will give us an IO instruction. Did you get it completely? Okay. Sir, you are not teaching theory of computation. I would like to. Yeah. I mean, TOC, not here, but I teach TOC also, but not in these sections. Okay, fine. Did you get it? Once again, just put it in a segregated manner. The thing is, we will have the combinations from 000 to 111. These are the opcode combinations. 000 to 110 are assigned to memory reference instruction. If it is 111, it is not a memory reference instruction. Then it is what? It could be either a register reference or an IO instruction. But it could be only one. So how to differentiate? Don't worry. Just go to the mode digit. Then ask mode digit, what are you? Mode digit will tell you that I am nothing. I am nothing if it is not a memory reference instruction. So at that time, mode digit is available to us. Okay. If there is no addressing mode, we will use this mode digit to differentiate between register reference instruction and IO instruction. A combination of 01111 will give us register reference instruction. A combination 1111 will give us IO instruction. That's it. Okay. So this is how you are going to identify the instruction format. Okay. From 000 to 110, anything is a memory reference instruction. But when it comes to 111, just observe the mode digit. If the mode digit is equal to 0, then it is a register reference instruction. If the mode digit is equal to 1 followed by 111, then it is a register reference instruction. That's it. Okay. Now, let us, discuss all the instructions completely. Anyhow, I'm not going to explain you end and, first one is end, 000 is end, 001 is add, and the third one is load, fourth one is store, fifth one is BSA, sixth one is BUN, seventh one is ISA. There are a total of 7 instructions in our system, right? Let us understand what is end. And of course, I told you that we are not going to discuss these two, right? Now we'll start with load and store. What is load? Let us say that load 450. This is the instruction. Okay. If it is load 450, what will happen? The value which is available at the memory location 450 will get transferred to accumulator. Load instruction will transfer the contents of the memory locations to accumulator. Okay. What is store? Store is opposite to load. Contents of the accumulator will get transferred to the memory address which is specified within the instruction. Okay. Now there is something called store. What is store? Okay. Load transfers the contents of this memory location to the accumulator. Store transfers the contents of the accumulator to this memory location. Just vice versa. Did you understand this? The load and store instruction. The difference between load and store instructions. Did you get it? I will put it here. Accumulator will get the value from M of 450. Okay. Next, this is nothing but M of 450 will get a value from accumulator. Okay. Now let us understand BSA and BUA. Okay. I am going to take some time to explain you guys about these instructions. To explain you completely about these instructions. For this, I want you people complete attention, because you're going to understand what is going to happen in your programming language when you try to execute different kinds of high-level language instructions. You're going to have a complete clear-cut idea, the other dimension of your program execution paradigm. Okay, I'm going to show the actual dimension of the machine language instructions when you're going to execute a high-level language program. Okay, let us stay focused. Now, let us say that this is my main memory. Yeah, this is my main memory. Okay. Now, let us see that. I'm executing one instruction. This is 23rd instruction, let us say. Okay. And for this, the program counter value will be 24. I don't need to explain you this, right? The current instruction is 23. CPU is executing 23rd instruction. CPU is executing where? Which instruction? 23rd instruction. If the 23rd instruction is the current instruction, the program counter is equal to 24, right? Yes or no? Good. Now, for any instruction, at the end of the first instruction, after the end of the current instruction, next instruction will get executed. This is the thumb rule. After executing the current instruction, we are going to execute the next instruction. This is, most of the times this will be true. Okay. But sometimes the programmer may want to go to a subroutine, may want to call a subroutine. Okay. For an example, you want to call a function from another function. Okay. You perform calls, right? You're going to call the function call. You're going to make the function call. Yes or no? So at that time, when you decide to call a subroutine, next instruction will not be executed. Obviously, this is the thing that you need to understand. Obviously, I know that you also know about it. If the current instruction is just nothing but a call to another subroutine, the next instruction will not get executed. Okay, for an example, here the current instruction is call 450. Okay, the current instruction is call 450. When you say call 450, this is just nothing but calling a subroutine. In your program, you just call another routine from a routine. For an example, you written a main. Okay. In main, you declared a function f1. In the function, you have written something. Okay. After that, you just called f1. Here you called f1. This is just nothing but a call instruction. Okay. So, when you execute a call instruction in a high level language, it will get translated to BSA instruction. You got my point? When you execute a call instruction in the high level language, it will get translated to BSA instruction in the machine language. Okay, so it is just nothing but BSA instruction. The equivalent instruction to call instruction in the machine language is BSA. BSA stands for branch and save the return address. Lokesh Parab has something to say. After every call, then it will point to the PC of the next instruction. Every call is complete. I did not understand. Lokesh Parab, what you're talking, what you're asserting, I did not understand. Just could you please explain me what is every call is completed? What is every call is completed? Could you please tell me about this assertion of every call is completed? Okay, fine. Let me tell you now. In our case, we do have a call instruction. When in your high-level language, when you call, when you execute a call instruction, it is going to get translated to BSA. BSA stands for branch and save the return address, which means that we are branching to a subroutine. Got me? Sir, could you please say what is the function of BSA again? Yes, stay focused. That is what I'm explaining. I did not finish with BSA. BSA is going to take some time. Okay, so we're not going to finish in this week. Maybe it will get passed and next week going to resume. But the thing of BSA is, the thing with the BSA is, BSA stands for branch and save return address. Got me? Write it somewhere. Branch and save the return address. What is branch and save the return address? Stay focused here. BSA stands for, it is just nothing but a call instruction, right? We are calling a subroutine. Okay, where the subroutine is originated? Okay, subroutine is originated at 450. The address part of the instruction in associated to BSA will tell you where the subroutine is located. So, the control of the computer system will go to 450. In this, the actual subroutine is available. Are you understanding this or not? Again, just let me put it this way. You executed a call instruction. Call instruction is nothing but you are calling a subroutine in your programming language. When this getting translated to machine language instructions, the equivalent instruction to the call instruction is BSA. BSA stands for branch and save the return address. What is branch? Branch to subroutine. Branch means branch to subroutine. Where the subroutine is available, don't worry. Subroutine will be available in the address part of the instruction. Subroutine's address is available in the address part of the instruction. We need to branch to the 450th location in which the actual subroutine is available. But this part is save the return address. What is save the return address? We need to save the program counter value, because after the branch has been made, then we start executing the subroutine. Sooner or later, subroutine will get completely executed, right? When the subroutine gets executed, we need to return back to the calling routine. The routine which calls is subroutine. Did you get it? That's it. Branch to the subroutine's address. Don't worry where is the address. Address is available in the address part of the instruction. It is going to give you subroutine's address. But before you branch, you need to save the return address. What is the return address? The return address is nothing but a program counter value. Yes, I told you for several times that either you call it as a program counter value or a return address. Both are one and the same. Why we need to save the program counter value? Program counter value is going to give you the instruction which was suspended. After executing the subroutine, from where we need to start again. Got me? So before you branch to the subroutine, you save this program counter value somewhere. 24 has to be saved. Okay, I saved it. Then I branch it to 450, in which the subroutine is available. So subroutine is, let us say, from 450 to 460. Okay, subroutine is finished. Okay, subroutine is spanned in 10 locations of the main. Now the subroutine is finished. Still, it is important to save the program counter value, because if you don't save the program counter value after executing the subroutine, how you will be able to go back to the routine which was suspended? Got me? Because after executing the subroutine, we need to return back. If you can't save the program counter value, you can't return back. Did you get it? So, function returns will only be possible if you are able to save the program counter value, which is also called the return address, when you execute the call instructions. This is all about branch and save the return address. Did I make it myself clear? Kirti, any doubt so far? Very good. Lokesh, are you sleeping or what? Good. Now, you got it already. What is BSA? Branch and save the address. Branching to the address part of the instruction. Address part of the instruction is given to an address in which the subroutine is originated. After finishing the subroutine, where we'll go? We will go to the location where the return address has been saved. Now, our duty is our job is to identify a specific and a good location in the computer system for an efficient storage of the program counter value. Okay. Now, our job is simple and complex. I'll tell you why it is simple, and I'll also tell you why it is complex. It is very simple because we do require one storage area. That's it. It could be a buffer or a memory location or any other thing. That is, we just need to save the program counter value. We don't need to save a table or database or something else. Only the program counter value must be saved. So we want a simple location. Did you get it? So in that term, in that aspect, this is very simple. Okay. But I'll tell you the complexity in identifying a storage provision for this. The complexity is, are you listening? Are you listening? What is the complexity? I will ask, okay. I'll put it this way. I will ask Lokesh to give me a box. Okay. Mr. Lokesh, just go to your computer system. From the computer system, just get me one box so that I'll put my program counter value in that box. Immediately, Mr. Lokesh has gone to his computer system. He identified a box. Okay. It could be a register or a memory location. That is his wish, because I have given the decision making power to him itself. Okay. So he collected one register or a memory location. I don't know exactly, but he collected one buffer and he gave me the buffer. He asked me, sir, you can put your program counter value here. Okay. So fine. In that aspect, it will be very simple. Now I'll tell you from where the complexity arises. Now I put my program counter value. What is the program counter value? 24. Mr. Lokesh has given me the box here. This is the box. Okay. This box could be a processor's register or a memory location. Okay. But this is a single provision. What did I put? Before I go to 415, I saved my program counter value here. Okay. Here you can understand. As this is a single entity, did you get the point? You see any problem here? You have to see the you are the best programmers in the world. You need to tell me what is the exact problem. What if this subroutine calls another subroutine? Again, I need to save the program counter value, but you do have a single box. You got my thing. Did you understand my point? I asked Mr. Lokesh Bharat to give me a provision to store my program counter value. He got me a box. We named that box as a program counter saver. Okay. But this is a single provision. Did you get it? How we can save the multiple program counters values? Okay. If this function calls this one, if this called function strictly return back to the calling function, this is feasible. This is pretty much practical and sufficient. But what if this subroutine calls another subroutine? What if there is a nested subroutines? Did you get my point? I'll tell you. See, I did not talk about the box. I am going to explain you. Okay. So we need to identify a proper location in which even the nested subroutines also should be supported. Okay, a single provision might not be sufficient. We do require multiple provisions. Okay, so that even if there is a nested subroutine, there won't be any chaos occurs. I mean, the previous program counter value should not be replaced. Did I make it myself clear? Yeah. No. This thing is, I'll tell you. Only the perception is complex. After we figure the things out, it will be very simple. You yourself will tell me that, sir, this is very simple. First of all, we need to think what is the problem. Problem always appears to be very complex indeed. Okay, constructing the building itself, architecture, this is very complex. But once after the building has been constructed, when you enter into the rooms, you understand the simplicity. Okay, being the architect, we need to make it simple. we are going to discuss how to design this provision in the very next session. This provision is going to save the program counter value. Even if there are multiple program counters values to be stored or saved, the previous program counter value won't be erased. Simply you will tell me after designing this, rather after identifying this, how simpler that will be. You got me? Okay, so that's it for the day. So far what we discussed about the memory reference instructions. In the memory reference instruction, we already discussed a few instructions. Now we are in BSA. BSA stands for branch and save the return address. In branch and save the return address, we won't execute the next instruction because we are going to branch to a subroutine. But before that, we should be able to save the program counter value. Okay, if you want to save the program counter value, we need to have a provision. But provision must be identified very carefully because in case of a multiple subroutines, we should ensure that the previous program counters values should not be erased. Thank you so much. Okay. Yeah. Since the topic is very nice and thank you so much. And yeah, same day, same time next week. Okay. Till then, take a break for 1 week.